Well, hi, everybody. In this video, I'm going to give you a quick introduction to linear algebra. Linear algebra is a very useful branch of mathematics. It has wonderful applications to differential equations, first and foremost, but also in many other areas, computer science, computer graphics, economics, you name it. There's a lot of places where linear algebra is a very important subject. Now, this is a little bit different than calculus. This is not the same kind of math that you may have been used to in some of your previous courses. And so if you've never seen this material before, it's going to feel a little bit different. I'm going to take the subject right from the very top. I'm not going to make a lot of assumptions. I'm just going to start from the basics and kind of give you a quick overview. If you've seen some elementary linear algebra ideas before, this video might go fairly smoothly, fairly easily for you. I'll try to keep it interesting, but I just want to take this time to present the material from the very outset with really no background assumptions needed. In general, we can talk about matrices and systems of equations. This is a part of linear algebra, and I'm actually going to start with the systems of equations portion of the title of this video and kind of work from there. Let me start by just making the definition of what a linear equation is. That's really the starting point for this conversation. So as a definition, we're going to start as follows. A linear equation, linear equations are the most simple type of equation that you can discuss. And so we'll start with the definition of that. This is an equation that has the form. Let's write down the form of a linear equation. It's going to look something like the following. A1 x1 plus a2 x2 plus ... plus an xn equals b. Something like that. And in this notation, I want you to recognize that the a sub i's, those are constants. B is also a constant. So those are values that are given to us. Those are numbers that are fixed. And the unknowns, what I like to call the unknowns in this system, are these x sub i's. Those are the unknowns. Those are what a mathematician would generally want to solve for. I would like to solve for the unknowns in this linear equation. Okay? Of course, we will generally not just be interested in one linear equation, but an entire collection of them. And as another definition here, a collection of linear equations. A collection of linear equations is called a system. So you see the word system up here. It is called a system of linear equations. And so it is often an entire system that we will be working with. We will not just have one equation, but we might have an entire collection of several of them. Okay? Let me just write down an example of a linear system just to kind of warm us up to this idea. Again, maybe some of you have seen these ideas before. You certainly have seen linear equations before. You may just not have been focusing so much on their properties or the theory behind them. Instead, you might have been given a system of equations. Let's write down an example here. Maybe I have negative 3x plus 2y plus z minus w equals 5. That would be a linear equation. You see, I have a lot of constants in the equation, and I have unknowns. Now, up here, I was calling the unknowns these x sub i's, but if I have, like, say, exactly 4 of them, I might just label them as x, y, z, and w, like I've done here. Okay, and then maybe we have another equation, 2x plus 2z is equal to 3. That's another linear equation. And maybe we have another one, negative y plus 5z plus 2w equals 0. This is just an example of a system of linear equations. And as I was talking about earlier, a lot of times the goal, when you have a system of linear equations like this, the goal is to solve, if possible, let's say if possible, it's not always possible, solve, if possible, for the unknowns. I could probably give you a very simple example to show you that it's not always possible to solve for the unknowns in a linear system, right? So as a quick example of another linear system we could look at, maybe you have, x plus y equals 1 and x plus y equals 2. The unknowns are x and y. You're not going to be able to find values of x and y that solve all of the equations in that system. This is a linear system. This system, there's actually a name for this. This system has no solutions. So when we do solve for the unknowns, we call them solutions. Not every linear system has any solutions, and there's actually a definition for that as well. Sorry, there's a lot of definitions here because we're kind of looking at a very new topic, so we have to kind of set the groundwork and get the basic language together here. But the idea is that a linear system with at least one solution has at least one solution, it is called consistent. In that case, it is called consistent. Otherwise, if it has no solutions, otherwise, it is inconsistent. So inconsistent just means no solutions. The system at the top of my board right now, x plus y equals 1, x plus y equals 2, that is an inconsistent system because there are no solutions for x and y. As long as there's at least one solution, then we're going to call that system consistent. Okay. So we kind of know what a linear system is now. It's just a collection of linear equations. The goal is to try to solve for the unknowns in that system, if possible. If it is possible, that means the system is consistent. Otherwise, the system is inconsistent. Okay. We're going to talk more about how to actually do the solving process later. This video is much more elementary. We're just trying to kind of lay the groundwork and set up some basic definitions. Speaking of that, in order to really work with these linear systems, these systems of linear equations, it turns out that it's kind of convenient to just keep track of the numbers that are in the system, okay, and not write out all the equations all the time. And that is where the role of matrices, or in other words, a matrix, comes into play. If you remember, the title of this video is Matrices and Systems of Equations. So the way that matrices sort of enter into this picture is that they give us a notational device for sort of keeping track of our linear systems. So let me write that down, and then I'll put a formal definition of a matrix down for you, okay? So just to kind of lay the groundwork here, I'm just going to make a note. It's kind of worth recording this note as well, that we will use matrices. So the word matrix has a plural, and the plural of the word matrix is matrices, right? To study these linear systems that we've just been talking about. Okay, so we're not actually going to get around to solving the linear systems today, but we're at least going to kind of set up the framework for it. We're going to get the notation in place, and part of that involves the concept of a matrix. So let me write down the definition of a matrix, basically. A matrix will always have a particular size, so I might call it an M by N matrix. So this is the way we would read this, guys. An M by, so that little X means by, an M by N matrix. It's usually written with capital letters. So whenever I want to write down a matrix, I will usually use capital letters like A, B, and C. Things like that generally are good notations for a matrix. And it is simply an array. It is an array, I'll explain that in a moment, of numbers, or it doesn't have to just be numbers. It could actually be an array of functions. Okay, so it's an array of numbers or functions arranged in m rows and n columns. Okay, so we're talking about just a block of numbers or functions. There are m rows, by the way, just to be clear, the rows go sort of sideways, horizontally. There are m of those, and then there are n columns. The columns are going up and down, okay? So we have to keep this straight. Sometimes rows and columns can get a little bit twisted up in our heads. So just to keep it straight again, the rows go horizontally, m of those, right? And the columns are arranged vertically, and there are n of those. Let's just write down an example of a matrix, in case there may be some of you who haven't really seen this idea before. I like to use square brackets to kind of create my space or my block for my matrix. And then we just throw some numbers in here. In this case, numbers. It could be functions, but I'm just going to use numbers on this first example. Could be something like this. Okay? So I'm just going to copy this down really quickly here. Something like that. That's an example of a matrix. Just to test you on this, we could talk about what's the size of this matrix. In other words, what's the m by n here? The number of rows, remember the rows go horizontally. That's just the m value. So for this matrix, m is 3, right? So that's the m value. And it is m by n. And the n value, how many columns are there here, up and down? That would be 4, right? So this is a 3 by 4 matrix. And sometimes I'll even denote that over here. I'll write like something like 3 by 4 right next to the matrix, just to kind of emphasize what its size is. Now, if you want to stop and pause for a moment, I did not just grab this matrix out of the sky randomly. I have a pretty small whiteboard, so I had to do a little bit of erasing. But maybe in your notes, you can see where this matrix might have come from. Where did I grab these numbers from? Take a look at your notes if you want to. You can pause the video, give it a little bit of a glance. But I'm going to tell you right now where these numbers came from. They actually are the coefficients of the linear system of equations that we put down as an example just a few minutes ago. And this is what I was talking about. We will use matrices to study linear systems. I'm going to take my linear system and I'm going to convert it into a matrix. Each row of this matrix is sort of home to the coefficients of one of the equations in that system. So this is actually called the matrix of coefficients. So if I want to give a fancy word to it, it's called the matrix of coefficients of the linear system. Of the linear system above. So again, it's not on my board right here, but if you just look back, scroll back or look back in your notes, just a short distance back, you should find the linear system that has these coefficients. Now, one thing you might notice about it, though, is that this matrix is not keeping track of the numbers that were on the right-hand side of all of the equations in the system. So, like, for example, up here, if we look at the example that's on my board right here, you see, for instance, that the matrix of coefficients would just be, I'll call that capital A again, would just be 1, 1, 1, and 1. But notice that the right-hand side values, the 1 and the 2, are not referenced by the matrix. So we have a little fix for that. Sometimes we actually do want to keep track of everything, not just the coefficients on the left side. So let me take a moment and basically show you what the augmented matrix for a linear system is. Okay, so what we can do is we can also form, or we can also consider the so-called augmented matrix. This is usually written with a sort of a pound symbol next to the matrix. So this would be like A sharp. And going back to the, let's use the larger example here at the bottom. What we would do, guys, is we would take the original coefficient matrix. I'm rewriting that again. But we would now add one more column over here on the right. And I actually highly recommend that you use a bar here to sort of separate this far right-hand side. So this right-hand side right here, this is sometimes called the right-hand side vector. Okay, and meanwhile, here's the original matrix of coefficients. And taken together, if we take the matrix of coefficients and we augment it with the right-hand side values, in other words, the right-hand side vector, we obtain this A sharp matrix, which is called the augmented matrix. Notice, of course, that the size of the augmented matrix, right? The size of this one is now, it's no longer a 3x4 size. It is now a 3x5 size because I have one more column that I have added onto the matrix. Okay. I hope this is all making sense. If you need to take a moment and pause, think about things a little bit more. In the meantime, that's totally okay with me. Jot down any questions you might have so you can send them to me. That's also fine. Just as a notational point, this is a brief item I just want to mention here. Sometimes we like to sort of pick off a particular slot in this matrix, a particular entry of the matrix. So I just want to have a notation for that. So the entry in row I and column J. So if I pick a particular row and column, right? A row goes horizontally, a column goes up and down. If I sort of line up a row and a column and I look at an entry that's in a particular row and column, this is often denoted, just for the notation, we will use a notation. It is double subscripting now, which is A sub ij. Notice that we always put the row values first and the column values second. That's standard. Everybody does it that way. So in the matrix that's on my board right now, maybe just for practice, you guys could pause the video here and just work out a couple of these things. You know, so what would be, for example, A24 and A32? Why don't you pause the video and see if you can just fill those in, just based on this matrix that's right here, A sharp in the middle of my board. Okay, so for A24, I'm looking at row 2. Row 2 is in the middle here, the second row, and I'm looking at column 4. If I just sort of look at where those guys intersect, I see that that is just 0, right? Whatever number is in that slot of the matrix is denoted with A24. A32, let's try that one. That's row 3, excuse me, row 3 and column 2. That would be a -1. Pretty easy, right? Pretty easy. Okay. So guys, we started this conversation talking about systems of linear equations, and we've now kind of drifted over into the realm of matrices. Matrices are just blocks of numbers or functions that sort of keep track of the coefficients or the values that you see in a system of equations. That's the connection between the systems of equations and the matrices. Connection between the systems of equations and the matrices. But I'm going to set the systems of equations down for a little while. And I'm going to spend most of the rest of this video talking just about matrices, just in their own right. What is interesting about matrices? Okay, so I'm going to actually might just start all over here at the top, right? I want to just talk a little bit about what are some things that you can do with matrices. So I'll call this operations on matrices. Operations on matrices. What are some things that we can do with matrices? So there's actually a lot of things. I'm just going to highlight a few things right now for you. The first one is we can do something called a transpose. We're going to see this quite a bit. It's actually quite important as well in the applications of linear algebra. So it's worth thinking about this a little bit. When I transpose a matrix, what I'm going to do is I'm going to interchange rows and columns. In other words, I'm going to swap them. I'm going to interchange the rows and the columns. What that does is, just to kind of draw a visual behind that, let's suppose that my original matrix is M by N, M rows and N columns. When I do the transpose, I'm going to turn rows into columns and columns into rows. There's a notation for this. We write it as an A with a little, almost like an exponent. It's not really an exponent, but I write it with a T after it. So that means I'm transposing the matrix. And the size of this resulting matrix, because I've reversed the roles of rows and columns, the new matrix would have N rows and M columns, right? So the M and the N get switched. So in our example from above, again, I don't have it. Well, let me write it down again here for you. So if we take the original matrix from our example earlier, we had -3, 2, 1, -1 in the first row. The second row was 2, 0, 2, 0. And the third row was 0, -1, 5, 2. If I transpose that, so this was a 3 by 4 matrix, yeah, from our earlier example. Now the transpose is going to be 4 by 3. So the first row becomes the first column. The second row becomes the second column, and the third row becomes the third column. It's going to look like that. It is now a 4 by 3 matrix. The original matrix was 3 by 4. The new matrix is 4 by 3. So this is the first operation. I haven't really given you reasons why we would do this yet, but it does come up a lot, and we will see that. It's the first pretty standard, pretty familiar operation that we can do on matrices. The second thing I wanted to talk about is that we can do calculus. So we can do calculus on our matrices. This will be a little more interesting if the matrices actually have functions in them. So I talked about that earlier, that a matrix could have functions inside of it. Let me use a different letter for this matrix. I'll call it capital B. And let's just suppose that it has e to the 2t, negative sine of t, 3, and ln of t. That's a 2 by 2 matrix. It's actually, sometimes they'll call it a matrix function, because the entries are no longer just numbers. There is one number here, but all of the other entries are actually functions. And so when I say calculus, when you think about calculus, what are the sorts of things that you can do with calculus? As soon as I'm viewing this as an actual function of, in this case, t, well, I can take the derivative of it. So I can differentiate. So I'll call this item A. And differentiate. So I can do derivatives, right? So in this example, if I took the derivative of the function b of t, well, how would you imagine doing that? There's no surprise, guys. You would just literally take the matrix B and take the derivative of every single entry. right? So the derivative of e to the 2t is 2e to the 2t. The derivative of negative sine of t, well, that's negative cosine of t. The derivative of a constant, we know that that's equal to 0. And the derivative of the natural log of t is just 1 over t. These are just from calculus, right? And so we're taking the derivative of a matrix slot by slot. That's how it's done. Okay, so that's differentiation. I guess maybe I need a little more room. Let me come back up here. Going right along with derivatives, of course, would be the opposite concept, which is part B here, integration. Integration, so we can also integrate a matrix function. That might look something like this, integral of b of t dt. And in this case, we're simply going to integrate all 4 entries of this matrix. So the integral of e to the 2t of e to the 2t. However, by the way, this is an indefinite integral right now. I could, of course, have limits of integration. You learned in calculus, I'm sure, that you can talk about integrals that do have limits of integration. Those are called definite integrals. Or something like this, which is an indefinite integral, no limits of integration. And whenever you have no limits of integration, you always have to add that plus c. Do you remember that for an indefinite integral? And because I'm going to have different constants potentially in the different slots of the matrix, I'm going to call that constant C11. Instead of just writing plus C, I'm going to call it plus C11. It's kind of consistent with our notation for the 1, 1 entry of the matrix. Let's see, when I integrate negative sine of t, I will get cosine of t. And there's a constant of integration there as well, but it might not be the same constant. So I'm going to call it C12. Okay. We can integrate the number 3. That, of course, gives me 3t. And again, we have another constant of integration. I'll call it C21. Finally, we have to integrate the ln of t. That one may not be right off the top of your head. It is done using integration by parts. I'm just going to tell you what it is in case you're not sure. It's t ln of t minus t. You can always check that. And then we add C22 to that. Okay. So we have these constants of integration that show up. It would actually be perfectly fine if you prefer. You could just focus on the antiderivatives themselves first. And then what you could do is you could take the C11, C12, C21, C22, and just write it as a giant plus C, where this plus C is not a number anymore, but it's a 2 by 2 matrix of numbers. Right, so that's integration in a nutshell. You can do it slot by slot, just as you naturally probably would think to do. Same thing as taking derivatives slot by slot as well. Okay, these are just 2 examples of some ideas from calculus. Right? Of course, calculus is all about limits, and of course, the applications go on and on and on. So there would be no reason why we couldn't spend a lot more time talking about calculus applications of matrices. But I'm going to leave it at this for now because I want to keep my time relatively shorter. So we can do transposes. Okay, transpose, that's where you switch the rows and the columns. We can do calculus. And now there's one more thing I'm going to do. By the way, I'm going to erase the whole board, so feel free to pause if you are not caught up quite yet. So I'm going to get rid of what's up here so that I can start fresh, because this next point is going to take a little bit more time. The third operation on matrices that I want to talk about today, guys, is algebra. This is actually the one that we will be using the most. We will use transposes somewhat, and occasionally we may have a reason to do a derivative or an integral of a matrix, but algebra is really where it's mostly at. And I'm really thinking here, guys, very, very simple. I'm thinking about things like addition, subtraction, multiplication. So I'm just writing notations for standard operations of addition, subtraction, multiplication. And then I'm going to add something in here that I'll explain shortly, which is called scalar multiplication. And I'm not actually going to talk about division right now. Turns out we don't have an idea of dividing one matrix by another. So I don't want to mislead you into that right now at all. We're just going to focus on addition, subtraction, multiplication, and then something called scalar multiplication. So let's talk a little bit about each of those. Let me start with just addition and subtraction. If I would like to add or subtract matrices, I can do that as long as the matrices have the same size, m by n, right? The number of rows and columns of the two matrices has to agree. So let's just say it this way. Given two matrices, A and B, of the same size, let's just say it's m by n, so it's just any two matrices of the same m by n size, right? We compute A plus B and A minus B. So I'm talking about addition and subtraction of two matrices right now. And the most important thing about this is that we carry this out slot by slot. It's totally common sense. We just line up the different entries of the matrix and we add and subtract them in the corresponding slots, okay? It's pretty much the natural thing that you would normally want to do, right? So just, I won't spend much time here because this is pretty intuitive, but let's just say we had, you know, the matrix A, 1, 2, 3, 4, 5, 6, 2 by 3, right? 2 rows, 3 columns. My second matrix, if I want to do addition or subtraction, it has to be the same size. Maybe 3, 0, 6, 1, 4, 2. If I take those two matrices, well, then it's very easy. This is just for an example. If I wanted to add them together, I would just do it slot by slot. What do I mean? Well, the upper left slot, right? The upper left corner, 1 and 3, we add those together and get 4, right? The upper middle slot is 2 plus 0, which is 2. The top right corner is 3 plus 6, which is 9. The lower left corner, 4 plus 1, which is 5. I hope I'm not boring you too much. The middle on the bottom is 5 and 4, which adds up to 9. And the lower right corner is 6 plus 2, which adds up to 8. Very simple, right? We could just as well do subtraction, okay? So there'd be no reason why we couldn't also do subtraction. If you want to practice this, guys, go ahead and pause the video and I'll let you do it and then we can check. But I'm going to very quickly do it and hopefully I'm going to do it right. But these are the values that I'm going to come up with when I do subtraction A minus B. Of course, A minus B is not the same as B minus A. We know that even with regular numbers, when we subtract, the order of the subtraction makes a difference. Okay, so addition and subtraction, very simple. Okay, let me skip over multiplication for a minute. I want to talk next about the scalar multiplication. This is where we take a matrix and we just want to multiply it by a number. Okay, this turns out to be pretty easy as well. So let me talk here about scalar multiplication. Okay, just scalar multiplication. So here the idea is given a matrix capital A and a scalar, which I'm going to call K. So a scalar just means a number, right? Right? Then we can form K times A. This is the scalar multiplication operation. We take the matrix and we scalar multiply it by some number K by multiplying each entry of capital A by whatever K was. Okay. So again, it's a very simple idea. If we go to an example, let's go right back to the same matrix we were just using a moment ago. 1, 2, 3, and 4, 5, 6. If I gave you a scalar, let's just say K was 5. It's just a number, right? Well, then in that case, we could very quickly calculate K times A. All we have to remember to do is multiply every single entry by 5. 5, 10, 15, 20, 25, 30. That's the answer. Here you only have one matrix. It doesn't matter what its size is. If you want to throw a scalar multiple through it, we can do that. That's the second operation here. Great. Hopefully clear. By the way, there's nothing wrong with k being a fraction or a negative number, or it could be 0. If k was 0, then of course, when you do the scalar multiplication, you completely zero out every entry of the matrix. It's just a matrix of zeros at that point, but it's allowed. You can do that. Okay. Great. So I've talked about most of these operations. I want to wrap this up, guys, by talking about what's probably the one that's maybe the hardest to understand, at least when you're first learning the material, which is regular matrix multiplication. It's a little bit more complicated than just some kind of a slot by slot thing. So we have to be a little more careful here. There is a reason why we multiply matrices in the kind of weird way that I'm about to show you. But let's talk just for a minute about this. So multiplication. How does this work? Well, the first thing that's weird about it is that the two matrices don't have to have the same size to begin with. The m by n, right, the number of rows and columns, they don't have to be the same for the two matrices. So let's get the dimensions or the size of the matrix figured out first. Given the matrix A, and I'm going to assume that that matrix is m by n, and another matrix B, and here's the important thing about B. The number of columns of A has to be the same as the number of rows of B. Isn't that weird? So the number of columns of the first matrix, which is the number n right here, has to match up. It has to match up. Let me get this space for myself here, right? These numbers have to match up. The number of columns of A has to match up with the number of rows of B. This is the important thing. If we have that set up to begin with, we're going to talk about how to multiply the matrices together. If these values do not agree, if the n here does not agree with this one over here, then we cannot do the multiplication. It's the same thing as if I tried to add two matrices that were different sizes. We can't do it. So the sizes of the matrices is actually a very important part of the requirements here. But given this setup, we can form the M by P matrix A times B. So in this case, now we can actually multiply the matrices. The size of the new resulting matrix actually is M, which is the number of rows of A, by P, which is the number of columns of B. So we're kind of using a little bit from both A and B to figure that out. I think the easiest way to show you how to form that product is with an example. I'm just going to do one. All over the internet, guys, you can find lots of examples of people multiplying matrices together. So if this one example isn't enough for you, by all means, I encourage you to look for some other examples too. This is the one that takes like a little bit of practice. It's not quite as intuitive as the other operations that we've just gotten done talking about. So I've written down the matrix A again. This time I'm going to make a different matrix B altogether. I'm going to just kind of start over with a new one. So it's going to look something like this. -1, 3, 0, 1. Okay, so there's my matrix A and B. And I am going to first decide if I can even do the multiplication. Let's check out the size of A, 2 rows and 3 columns, right? The size of B, see, B has 3 rows and 4 columns. These are the sizes of the matrices, and the very first thing that we notice is that the number of columns of the first matrix is in agreement with the number of rows of the second matrix. So I am able to do this calculation. How do we do it? How do we form A times B? Well, first of all, let's get the size right. According to this definition of matrix multiplication, the resulting matrix should be M by P. So M is 2 and P is 4 in our example here, right? This is M, this is N, this is N, this is P. It's supposed to be 2 by 4. How do I fill out the numbers in here? This is the thing that takes a little practice. If I'm interested in the 1, 1 position, the number that goes right here in the top left corner, I am going to grab the first row of A and the first column of B. Notice they both have the same number of entries. There's 3 numbers in the first row of A, and there's 3 numbers in the first column of B. Why do those match up correctly? That's because of the 3 and the 3 here and here. Right? This is the reason we need the number of columns of A to agree with the number of rows of B. Because what I'm going to do now, guys, with this row and this column, it's like a vector, right? This first row is like the vector 1, 2, 3 that you would have seen in calculus. And this first column is the vector -1, 2, -1. We're simply going to dot them together in the same way that you would dot 2 vectors in calculus. Remember how that works? We need to remember the dot product here. So 1 times -1 plus 2 times 2 plus 3 times -1, right? So -1 plus 4 plus -3. You getting that? I'm going across the row here and I'm dotting it with the column here. -1 plus 4 plus -3 is actually 0. It all cancels out. That's the entry in the first upper left corner. How does it change if I want to know the next entry over? Well, I'm still in the first row, but now I'm in the second column. So what I'm going to do is I'm going to keep the first row of A, but I'm going to dot it now, not with the first column of B, but the second column of B. I'm going to do the same thing, a dot product. 1 times 0 plus 2 times 1 plus 3 times 3. 1 times 0 plus 2 times 1 plus 3 times 3. That's 0 plus 2 plus 9, which is 11. It's 11, yeah. Hopefully I'm going slow enough here. If you've seen this before, it's probably natural. This is something that should and needs to become natural to you as we move forward in linear algebra. I'll go a little bit faster. When I want to find the entry in the first row and third column, I'm now going to dot the first row of A with the third column of B. That's going to give me 2 plus 2 plus 0, which is 4. Okay. And finally, when I dot the first row of A with the last column of B, I get 1 plus 0 plus 3, which is also 4. Awesome. Okay, we can do the same thing on the bottom row, except instead of using the first row of A, now I'm going to use the second row of A. I invite you to pause the video and try it for yourself, and then you can watch what I'm getting for the results. But this would be good practice. You're dotting the 4, 5, 6 with each of the 4 columns of B in order to lay out the 4 entries in the bottom row. Let's try it. Well, you try it. Okay, hopefully you've had a chance to pause the video and try it yourself. Let's just do it together really quickly. First entry here in the bottom left corner, -4 plus 10 minus 6. That sounds like that is also a 0. Okay. What about 4, 5, 6 dotted with 0, 1, 3? Well, that's 0 plus 5 plus 18. That should be 23. The next entry, 8 plus 5 plus 0, that would be 13. And the last entry, 4 plus 0 plus 6, which is 10. I went a little faster there, and that's because eventually, of course, we all want to be able to go a little faster with this. It certainly is not intuitive when you're first learning how to do it, so I don't intend to expect you to be quite this quick yet, but it is something you want to get very proficient at. I do want you to get very proficient at it. I want to kind of conclude this video with sort of one last observation, and that is the following. Let's just stick with this example for a minute and ask sort of a follow-up question here. I could ask you the question, what is B times A? In this exact same example. question would be, what is B times A right now? It's kind of interesting. Well, maybe you want to pause the video again and think about it for a second. Look at the matrix B. The size is 3 by 4. So this is 3 by 4 right here. And the matrix A is 2 by 3. Is there anything wrong with that? Remember, when we do matrix multiplication, we're taking an M by N matrix on the left, and we have to multiply that by an N by P matrix on the right. These two numbers do not agree this time. And so it's kind of a trick question, guys. The answer here is that this does not exist. We cannot do this calculation. We cannot do it at all. A times B, perfectly good. But B times A, in this case. And that leads to kind of a general observation, which is very important for us to understand, guys. In general, it is not true with matrices that you can multiply them in any order that you want. In general, A times B is not equal to B times A. A fancy math way of saying that is matrix multiplication. There's a word for this. Matrix multiplication is not commutative. It's not commutative. So this means that we have to be very careful with matrices, right? We have to be very careful. For example, let me just give you a really quick example. Well, actually, before I give you the example, let me make a quick observation. I'll just call this a little remark or a note. Even if A times B and B times A, even if they are both defined, even if they both do work, let's say, for example, that A and B were both 3 by 3. If A was 3 by 3 and B was 3 by 3 and B was 3 by 3 and A was 3 by 3, we'd have no problem with doing multiplication of both calculations here. It would all be legit. We wouldn't run into some kind of a contradiction like we had on that last example. But even so, it is usually not true that AB and BA are the same. We usually find that A times B does not equal B times A. This leads to some weird things that happen. Let me show you just one weird thing here, guys, to wrap up this video. Let's suppose that A and B were both, let's suppose they were both n by n. And I decided to add them together. Okay, that's no problem. I can add an n by n matrix to an n by n matrix. But let's suppose that I wanted to square that matrix. And by the way, when I square a matrix, it means the same thing as it does with regular numbers. It just means I want to take the matrix times itself. So when I square a matrix, it just means multiply it by itself. Now, to expand on this, on the right-hand side, right, what you would do normally is just FOIL this out. Yeah, that's how high school algebra works with variables. So you could FOIL this out. A times A, that's A squared. Then you have A times B, right? Then you have in the middle B times A. And then you have B times B, which is B squared, right? Normally with regular high school algebra, with regular real numbers, we would be combining these two terms in the middle. And we would just write it as 2AB. Probably sounds familiar, right? When you FOIL out a perfect square like this. But we can't do that here. This is as simplified as we are allowed to go. We cannot combine the AB with the BA because they're probably not the same thing, according to the remark up above here, right? So this is already as simplified as it gets. This cannot be simplified. Okay, it cannot be simplified. So guys, you can run into crazy stuff with matrices. You can have things like A, B, A cubed, B squared, A, B, A, B. Something like that. You can't clean this up. You can't just say, oh, I'll put all the A's in the front and all the B's in the back. Because that would be violating this general observation that, yeah, you normally cannot switch the order of anything around. So you do have to be really, really careful about that. Matrix multiplication, first of all, it's a little weird to begin with. I'm hoping that this whole dot product idea that I've started to outline in this video makes sense as a procedure, so to speak. Not only is it a weird process, it leads to some weird things that can happen with the algebra. So the algebra of matrices isn't quite as simple as just your regular algebra with real numbers, or the kind of algebra that you would have done in high school math or more elementary math courses. Okay, so we are going to have to be careful about this kind of stuff. Guys, I think this is a good place for me to stop for now. I've given you 3 operations on matrices. We've got transpose, we've got calculus, and we've got algebra. There's a whole lot more that we can say. I think I'll save it for another time. I'm going to leave it at this for now, but I really appreciate you watching the video. I hope it makes pretty good sense overall. And if you've got any questions, feel free to reach out to me. But thank you so much for your time, and I'll look forward to seeing you guys all again very soon in the next video. Bye for now.